Good morning, everybody. So we shall continue our discussion on photo detection little bit further, though we will not discuss it in detail. So last day we have discussed about PIN photodiodes and then PN and PIN photodiodes for photo detection, and there are various modes of detection, that is photovoltaic mode, short circuit mode, photocurrent mode, and reverse bias mode. Out of these, most popular for instrumentation purpose is the reverse bias mode. Often this resistance is not directly connected to the V bias, but it is connected through a transimpedance configuration, either using FET or transistor or op amps. The consequence of higher load resistance is greater sensitivity in terms of voltage VRL. However, it also reduces the speed of the detection, or time response is deteriorated because of the RC time constant. Now today we shall discuss about avalanche photodiodes. Those are popularly known as APD. So the principle is similar to that photomultiplier tube, that where we had used a lot of dianodes to amplify the number of liberated electrons. Here this liberation is done by a greater gradient in the depletion, field gradient in the depletion region, such that the energy carried by the carriers will be much more, and because of the higher energy it will liberate secondary carriers. So basically it converts each detected photons into a cascade of moving carrier pairs. This is achieved by applying comparatively much larger reverse bias. So with larger reverse bias, the carriers acquire enough energy to knock down secondary carriers. Sorry. conduction and band and valence band. This is the depletion region. This side is P, this side is N. This is the intrinsic zone. And now if a photon liberates a pair of carrier, electron and hole pair, because of the reverse bias, holes will be accelerated towards the P zone and electrons will be accelerated towards the N zone. Now, as the accelerated energy achieves enough power to knock down subsequent pair of this is the original one, so it has knocked down one electron, and correspondingly there will be hole will be also created here in the valence band, and that will be accelerated. Similarly, in this side also it may happen. The accelerated carriers lose or impact with some carriers in the material and thereby liberating another pair. So like that, this whenever the energy of the carriers is sufficient such that the impact energy corresponding to the generation of a secondary carrier is enough to overcome the band gap energy Eg, there will be secondary carrier pairs will be generated. So this process carries through a lot of times, so thereby we can have a sufficient amount of multiplication of carriers. This is the distance x. Generally, the ability of the electrons and holes to impact ionization are related to the reverse bias potential as well as the band gap energy. However, the ability of impact ionization is characterized by two ionization factors corresponding to the electrons and holes. The abilities of electrons and holes to impact ionize are characterized by the ionization coefficients. Okay, where is it gone? So impact ionization coefficients. Alpha E and alpha H. Those are basically, these are the probabilities.
Sir, I can't see your video. I mean the writing pad.
Oh, you cannot see?
You, sir.
Is it visible?
No, sir.
Oh. I think now it is visible.
Yes, sir. Yes, sir. Now it came.
Sorry. So these are basically the probabilities of ionization per centimeter. Performance of APD is typically given by the ratio K between the two ionization. Usually either alpha H is made higher or alpha E is made higher. So because if both are equal, then what will happen in both sides, the ionic current will flow and there could be a pocket of circulating current in the depletion zone itself. So that give rise to uh, accumulation of carriers which are not being efficiently collected by the external circuit. To get it collected by the external circuit, the holes need to be forwarded through the P zone and the electrons need to be forwarded through the N zone, and finally it will be collected by the external circuit of current measurement or voltage measurement. So therefore, if alpha H equal to alpha E is undesirable, because of ionic unstable ionic flow. And local current loop. Local current loop, to avoid the local current loop, often it is necessary that the depletion zone and this multiplication zone to be separated. Apart from this differential choice of alpha H and alpha E, if K much less than 1, that is alpha H much less than alpha E, then there will be directional avalanche. Avalanching takes place from P side to N side. This is often a desirable condition because the mobility of the electrons are higher. To avoid local current loop further, local current loop and also undesirable recombination inside the depletion zone, because if the multiplication factor is quite high, then the carrier density in the depletion zone will be much higher, and then the probability of the collision between the hole and electron will also be higher. So to avoid that, the absorption zone and the multiplication zones are separated. So the basic structure is now modified little bit. We have a heavily doped P-type and heavily doped N-type. Then we have lightly doped in between narrow P-type, and there is a multiplication zone, and in between there is a depletion layer. So if we see the field gradient, This is the field, electric field, reverse biased. Then the charge density, as we have seen for the PIN, here also similar. Because of the lightly doped P layer here, so we have a small accumulation of negative charges also at this point. So this is charge density, that is so typically if we take a structure of APD, which of course we are just representing the structure without discussing much detail of it. This is an APD of say indium gallium arsenide on top of a substrate of indium phosphide. Indium gallium arsenide detection performance is better compared to gallium arsenide or silicon in the infrared zone. Typically from 700 to say 2000 or 2200 nanometer or so, the response of indium gallium arsenide is available. But good response would be like maybe 0.9 micrometer, that is 900 nanometer to maybe 1.66 micrometer. So in this zone it will have good response. N minus means lightly doped. Then there is a grading of this indium gallium arsenide to control the rate of the absorption. And also the band gap energy. Then here lightly doped indium phosphide, because of a discontinuity in the band gap energy, charge will be tapped here. This is an anti-reflection coating of silicon oxide, whose reflecting index is between air and indium phosphide. This side is P plus INP, so the P metal contacts are here. And N contact, metal contact is below. This is a very lightly doped N minus minus INP, and this narrow zone is the multiplication zone. So, because it is very lightly doped, resistance will be very high. So therefore, the field gradient along in this zone would be quite high. So carriers will be highly accelerated here and then replicated. Typically, this layer is much narrow compared to the drawing. So it could be 0.09 or some nanometer. Micrometer, sorry. This could be say 2 to 5 micrometer. This grading could be 3 micron. Buffer INP could be 3.5 micron also. This would be also 2 to 3 micron. This together would be 3 micrometers. So this is the basic principle of avalanche photodiode. Lot of other aspects are need to be taken care of, especially to control the multiplication and absorption. But from operational point of view, as an instrumentation engineer, the major aspect of operating APTs in circuit is to remember that because of the very high density of carriers, APDs need to be cooled. If not by liquid nitrogen like the photomultiplier tubes, at least the thermoelectric cooling is necessary to have to get a stable gain, because with respect to temperature the gain may change drastically. And biasing voltage need to be clean, need to be high. There are APTs as high as 40 volt, 50 volt biasing. Clean means there should not be ripple in the DC part. Again, if there are change in the biasing voltage due to ripples, etc., it adversely affects in the multiplication. Typically, multiplication are of the order of 10 to the power 4, 10 to the power 5 also. So therefore, you can guess that such a high gain, if it is used in a device, little bit of ambient change in condition may drastically fluctuate its performance and becomes unstable. From operational aspects, of course, there are other, in general, noise in photo detection. There are several other kind of noise like dark current noise, short noise, etc. can be there. But first one is, first and foremost is the thermal noise. Thermal noise typically depends on bandwidth and temperature. So it could be like if the temperature in degree Kelvin is capital T and the bandwidth is V, then it is given by 4K TV by R. R is the resistance, path resistance. More bandwidth means basically the noise will be more. Then there is dark current noise. Dark current noise also depends on bandwidth. The RMS value of the dark current. E, charge of an electron, then B is the bandwidth, and ID is the dark current. So this is the dark current noise, again depends on bandwidth. There is another important noise is short noise. Short noise, the variation in the number of electrons in a time interval delta t is given by some distribution. So within a certain time of interval, the probability, there is a positive probability of getting certain number of particles. That's because of non-absolute zero temperature. This happens. This is the variation in the number of electron. Variation of the number of electron uh, in a time interval t. Time interval delta t is given by a probability distribution. If say alpha is the number of particles per unit time, or say alpha into delta t is the average number of particles, in a time delta t, then the probability would be a Poisson distribution. Getting certain number of particles. Certain number of particles, say n, then the probability distribution will depend, of course, in delta t, because it is alpha into delta t, and this value n, that is the expectation of this n number of particles in a time delta t. So it's given by p n delta t. The distribution would be exponential of minus square by something, and So distribution would be exponential function, then there would be minus. Of course, this will be square. The distribution band would be twice of alpha into delta t. There would be a normalization factor. One by we are doing with respect to alpha delta t. Twice pi will be there. I think it is alpha delta t. It need to be checked afterwards. Now, if n bar, now the mean n bar value n bar equal to say alpha into delta t in a time delta t, then this p n delta t would be 1 by 2 pi n bar exponential of minus, this is delta n, this is n minus n bar square by 2 n bar. So this is maximum of course because this is minus, so I think this will be 0, then it will be maximum. And SNR is given by signal to noise ratio for short noise is square root of alpha delta t or square root of n bar. So that way these are defined. Usually manufacturer of course give a combined noise equivalent power. Manufacturers specify a combined noise performance with noise equivalent power. NEP. So given all those figures, quantum efficiencies and say bandwidth, temperature, etc., one can estimate what would be the expected noise equivalent power. It can also be evaluated experimentally. Generally, it is done experimentally. While designing, it is estimated, but finally, the performance figure quoted by the manufacturers are statistically done by conducting certain amount of statistical experiment. So I think we will discuss further about circuit etc. of photo detection later while applications will be discussed. Next we shall discuss about another component, that is optical fiber. Again we will just discuss the basic or the fundamental of optical fiber and quickly go to the applications. I think okay. So optical fiber is an important component for transport of energy or the signal. So usually there are two types of optical fiber. I mean, in terms of the modes, those are called, there are single mode and multi-mode optical fiber. Single modes are having a small core, whereas multi-modes are having larger core. But then refractive index profile wise, they can be classified as step index and graded index optical fiber. Most of the theoretical analysis is simpler for step index optical fiber, so which is so this is the core, this is cladding. Core refractive index is slightly higher. This is N1 and this is N2. N1 is greater than N2. So if N1 is much greater than N2, so we can capture light from a very large angle. However, from instrumentation point of view, that is not so important. From illumination purpose, optical fibers, those are used for illumination purpose. This large acceptance angles are important because they can capture larger energy and also deliver larger power. However, for instrumentation purpose and communication purpose, usually this delta n, that is n1 minus n2, is very small, and the acceptance angle of light through this core, that will satisfy the total internal reflection condition, is uh, for a small angle. I think today there is not enough time to discuss a new topic, so I shall start tomorrow. Thank you.